My name is Rishabh and I'm from CSE AIML department. Today I'm going to talk about the topic state the principle of superposition from the subject ordinary differential equation and vector calculus. Mathematical definition of principle of superposition. In mathematics, the principle of superposition is formally defined within the framework of linear algebra and the theory of linear differential equation. A mathematical system or operator L is satisfying the principle of superposition if and only if it is a linear, meaning it simultaneously satisfies two fundamental properties, additivity and homogeneity. Additivity states that for any two inputs u and v belonging to the domain of L, the operator satisfies L of function u plus v is equal to L u plus Lv. Homogeneity states that any scalar constant alpha and input u and operator satisfies L of Lu alpha u is equal to alpha into Lu. Combining both conditions, the complete mathematical statement for superposition principle is L alpha dot u plus beta dot v is equal to alpha dot Lu plus beta dot Lv for all the scalars alpha, beta and all the inputs u and v. This combined property is known as linearity. When a differential equation, algebraic system or a physical model is governed by a linear operator L, then if u1, u2, u3 till un are each individual solution to the system, any linear combination of a form y is equal to c1 u1 plus c2 u2 plus c3 u3 till cn un is also a valid solution to a same system where c1 c2 till cn are arbitrary constant. This statement constitutes the core mathematical power of superposition principle. It allows an infinitely large solution space to be constructed from an finite state set of a known bias solution, dramatically simplifying the analysis of complex mathematical systems. The linear differential operator L and its properties. The mathematical engine behind the principle of superposition in ordinary differential equations is the concept of the linear differential operator L, which provides a compact and rigorously notation for expressing linear ordinary differential equation and verifying the validity of superposition for an nth order linear ordinary differential equation with a coefficient function a0x, a1x which goes till an x. The differential operator L is defined as L is equal to anx into d power n plus an minus 1 into x d power n minus 1 plus which goes till a1 into x into d plus a0x, where d is equal to derivative with respect to x denotes the ordinary derivative operator. D square is the double derivative with respect to x and so on. With the notation of the ordinary differential equation an into y power n which goes till the summation of a naught into y is equal to fx is written compactly as L y is equal to fx and homogeneously equation becomes Ly is equal to 0. The operator L is a linear because the derivative operator d satisfies d bracket open alpha u plus beta v is equal to alpha du plus beta dv for any differentiable function u and v and constant alpha beta. Since sums and scalar multiples of linear operators are also linear and the full operator L is equal to an into dn plus summation goes till a naught inherits linearity giving L alpha u plus beta v is equal to alpha Lu plus beta Lv. This one equation, the linearity of L, is complete and sufficient mathematical proof of superposition principle of ODE. To verify the superposition directly, if L of y1 is equal to 0 and L of y2 is equal to 0, then L c1y1 plus c2y2 is equal to c1ly1 plus c2ly2 is equal to c1 into 0 plus c2 into 0 which is 0, confirming that c1y1 plus c2y2 is also a solution. For the non-homogeneous case, if Ly1 is equal to f1x and Ly2 is equal to f2x, then L C1y1 plus C2y2 is equal to C1f1x plus C2f2x, meaning the superposition of the solution corresponds exactly to the superposition of their forcing function, a result of great practical importance when a forcing function is a sum of several terms. Homogeneous linear ODE and a general solution via superposition. The construction of general solution of homogeneous linear ODE is most direct and classical application of a principle of superposition in entire theory of differential equation. For a second order homogeneous linear ODE with a constant coefficient, the most commonly encountered type in physics and engineering are a of y double derivative plus b into y single derivative plus cy. The solution process begins by assuming a trial solution of the form y is equal to e power rx, which when substituted into the ordinary differential equation yields the characteristics equation of a into r square plus br plus c is equal to 0. This quadratic equation has two real roots r1 and r2, which may be real and distinct and real and repeated or a complex conjugates. Each root generates one solution by superposition. The general solution is linear combination. This divides it into cases. The case 1, the real distinct roots r1 is not equal to r2, y1 is equal to e power r1x and y2 is equal to e power r2x are linearly independent. So y is equal to c1 e power r1x plus c2 e power r2x. Case 2. A real repeated roots r1 is equal to r2 is equal to r. The two linearly independent solutions are y1 is equal to e power rx and y2 is equal to x into e power rx, giving y is equal to c1 into e power rx plus c2x into e power rx is equal to e power rx common c1 plus c2x. Case 3. Complex conjugate roots r is equal to alpha plus minus I beta. Using Euler's formula, e power I beta x is equal to cos beta x plus I into sin beta x. The two real linearly independent solutions are y1 is equal to e power alpha x cos beta x and y2 is equal to e power alpha x sin beta x, and the superposition gives y is equal to e power alpha x common c1 cos beta x plus c2 sin beta x. In all the three cases, the general solution is superposition of two linearly independent solutions with an arbitrary constant c1 and c2. For an nth order equation, the process extends naturally. The characteristics equation is polynomial of a degree n yielding an n roots, and a general solution is a superposition of n linearly independent solution. Y is equal to c1 y1 plus c2 y2 summation till goes till cn yn. The constant are determined by applying the n initial condition y x naught a single derivative of y x naught at up to y power n minus 1 x naught. The Wronskian testing linear independence for superposition. For the superposition of solution in linearly ordinary differential equation to produce a valid and a complete general solution, the individual solution being superposed must be linearly independent, meaning no one solution can be written as a constant multiple of another. If linearly dependent solutions are superposed, the resulting expression contains reductant information and misses the part of the solution space, making it an incomplete rather than general solution. The mathematical tool used to test the linear independence is Wronskian determinant, named after a Polish mathematician. For two functions y1x and y2x, the Wronskian is w of y1 comma y2x is equal to determinant of y1 y2, which is equal to the y1 into y2 derivative minus y2 into y1 derivative of that y1 derivative y2 derivative. For three function y1 y2 y3, it is the 3 into 3 determinant w y1 y2 y3 is equal to that of y1 y2 y3 y1 of derivative of y1 derivative of y2 and derivative of y3, and in the third row it is double derivative of y1 and the double derivative of y2 and the double derivative of y3. The key theorem states that if y1, y2 up to yn are the solution of linear nth order homogeneous ordinary differential equation on an interval of I, and if w y1 y2 up to yn into x naught is not equal to 0 for an even one point x naught belongs to I, then the solution are linearly independent on I, and their superposition y is equal to c1 y1 plus c2 y2 up to cn yn. is the complete general solution. For example, for ordinary differential equation y double derivative plus y is equal to 0, the solution y1 is equal to cos x and y2 is equal to sin x. Give w is equal to cos x into cos x minus sin x into minus sin x is equal to cos square x plus sin square x is equal to 1, which is not equal to 0, conforming linear independency. By contrast, if y1 is equal to e power x and y2 is equal to 3 into e power x, then w is equal to e power x into 3 into e power x minus 3 into e power x into e power x, which is equal to 3 into e power 2x minus 3 into e power 2x is equal to 0, conforming dependency. Superposition, this would give y is equal to c1 plus 3c2 whole bracket into ex is equal to cex, which is an only a one parameter family, not the complete general solution. Abel's identity further states that for a linear ordinary differential equation, the Wroxen satisfies Wx is equal to Wx naught into exponent of minus integral bracket open a n minus 1 by a n into dx, which is either identically 0 or never 0 on the interval, a powerful result confirming that linear independency of ODE solution is global property on the interval. Method of undetermined coefficient using superposition. The method of undetermined coefficient is one of the two principal techniques for finding the particular solution to a non-homogeneous linear ordinary differential equation with a constant coefficient, and it uses the principle of superposition when the forcing function fx is a sum of several standard form terms. The method applies when fx belongs to the class of functions whose derivatives are the same form, especially polynomials, exponential, sines, cosines, and their products. For such functions, a trial particular solution of a same functional form is assumed, substituted into a ODE, and the resulting algebraic equations are solved for unknown coefficient. The superposition connection arises directly and powerfully when fx is equal to f1x plus f2x plus till fkx is a sum of multiple terms by linearity of L if L p ypi is equal to fix for each I separately, then L bracket open yp1 plus yp2 plus till ypk bracket close is equal to f1 plus f2 till fk is equal to fx. So yp is equal to yp1 plus yp2 till ypk. The trial solution forms for each type are fx is equal to pnx, polynomial of degree n. Trial yp is equal to anxn plus an minus 1 x power n minus 1. The addition goes till a 1x plus a naught and reduces with factor of n minus 1. Fx is equal to a into e power alpha x. For this trial, yp is equal to a e power alpha x multiply by x power m if alpha is a root of multiplicity m of a characteristic equation. Fx is equal to a into cos beta x or a into sin beta x. Trial yp is equal to a cos beta x plus b sin beta x. Always include both. Fx is equal to e power alpha x into pnx. For this trial, yp is equal to e power alpha x bracket open a xn plus goes till a naught bracket close. If fx is equal to e power alpha x into bracket open px cos beta x plus qx sin beta x, trial includes both cosine and sine polynomial terms. For this, we'll take an example. Y double derivative plus 4y is equal to 3x square plus 2 sin x plus 5 e power 3x. 1. Find separately yp1 for 3x square, trial ax square plus bx plus c. Yp2 for 2 sin x, trial d cos x plus e sin x, and yp3 for e 5 into e power 3x, trial fe3x f into e power 3x. Then superpose yp is equal to yp1 plus yp2 plus yp3. This superposition splits one complex problem into three independent simple problems, each solvable by straightforward algebra, perfectly exemplifying the problem simplifying power of superposition. Variation of parameters. The method of variation of parameters introduced by Joseph Louis Lagrange is used to find a particular solution of non-homogeneous linear ordinary differential equation. Unlike undetermined coefficient, it works for any continuous function fx even with the variable coefficients. For equation double derivative of y plus px single derivative y plus qxy is equal to fx. If the homogeneous solution is yh is equal to c1 y1 plus c2 y2. Replace the constants with functions. Yp is equal to u1 x y1 plus u2 x y2. Using condition single derivative of u1 into y1 plus single derivative of u2 into y2 is equal to 0, and single derivative of u1 into single derivative of y1 plus single derivative of u2 into single derivative of y2 is equal to fx. Solving using Roxen, w is equal to y1 y2 minus y2 y1. Single derivative of u1 is equal to minus y2 into fx by w, and single derivative of u2 is equal to y1 into fx by w. The final solution is y is equal to yh plus yp. Limitation of superposition in ordinary differential equation. The principle of superposition applies only to linear ordinary differential equation. If any nonlinear term appears, superposition fails completely. Example where it fails. Double derivative of y plus y square is equal to 0. It crosses terms like 2y1 y2 appears. Double derivative of y plus sin y is equal to 0, which gives sin y1 plus y2 and not equal to sin y1 plus sin y2. Y into double derivative of y is equal to 1. Product makes it non-linear. For approximately linear system, superposition works only for small values, small disturbances. As value grow, non-linear affects dominant. Key conclusion. Superposition works only for linear ordinary differential equation. General solution is equal to homogeneous plus particular solution. The Wroxian checks independence of solution. Methods like variation of parameters and Laplace transform depends on superposition. For nonlinear ODE, use numerical or advanced methods. Thank you.